So I just realized this morning I didn't upload. I think I didn't upload to the YouTube list last class, but I will do that. So we'll have these all uploaded. Last time we talked about how to think about volumes. Just think of it as little Legos. Just you add up little tiny bits and you build up large regions. And then how do we describe the mass of an extended object? How do we do that? New concept that we have to define.
Mass density.
Mass density, right? What was the definition of density?
Mass density. Mass density?
Yeah.
Like the equations.
Yeah, what was it?
dm over dv.
What that says is you have some shape, you think of it as little chunks. If you increase the volume by a little bit, you expect the mass to increase a little bit. You just kind of grow it bit by bit by bit. So density is the rate of change with which the mass increases as you increase the volume. That kind of makes sense. And then we would turn that around and say the total mass is the integral of the density dV. So densities, sometimes I think of mass and charge as being physics quantities, and I think of volume and length and stuff as being geometry or math quantities, and I think of densities as a conversion factor which transforms physics into geometry or into math. Yeah?
You had like a 10x where
I have a pencil. Oh. Okay. Okay, so that's what we had before. Great. Then we had another quantity related to density, which is a new word for most of you, I'm sure, but we will use all the time. What was the new vocab word we had? Specific volume. So specific volume. So if you think about it, so if this is uniform, you can think of volume, or sorry, density as being mass over volume, as long as everything's constant, uniform. Specific volume, which I always use with a lowercase kind of curly v, is volume over mass. Or it's really, more precisely, the better definition is that specific volume is 1 over the density. And that would be true using calculus as well. Okay? So what that says is how much volume you get per kilogram. So this semester, it will be very convenient to give do all of our calculations and all of our results and kind of think of it in a per kilogram or per mass. So many joules per kilogram, so many joules per pound mass. And because of that, it will be more natural to do everything as a divide by mass rather than divide by volume. So specific volume. And for us, when we say things are specific, maybe with one historical accident, if it says specific, that means a per mass ratio. So if the word is specific, you do it that way. Okay? So that'll be common. Awesome. That's great. Okay, so we've talked about density, we've talked about specific volume, we've talked about volume and mass of a fluid. What's another concept which might be useful to define? Think about this room or swimming pool. No, a different concept, something we haven't mentioned yet so far. With a fluid, a variable. Temperature, yeah, temperature's a little common. We'll come back to temperature. You could do viscosity. We won't. Something more fundamental. Pressure. Pressure. Okay, so we're going to do pressure. We'll come to temperature in a bit. That will be very important. Viscosity we won't really touch this semester when you take fluid mechanics there. Okay, so pressure. What is pressure? You guys know? It's somehow related to a force, a push, yeah? So what I want you to do is take one hand, put it on the table. Okay, you can push down on it, right? You feel this pressure. What can you do to increase the pressure on your hand? Okay, using the same amount of force. How can you increase the pressure? Does everybody have a pen or pencil? Yeah, push the same amount with the, right? The pressure is going to go up. So pressure is related to a force, but it's actually a force, and it's the way the force is spread over the area. So it's like the force per unit area. That's pressure. So pressure is the force per unit area. Now, the more precise way you would say that is, imagine you've got a plate, okay, and you've got a fluid that's pushing on it, and imagine you build the plate up by adding little postage stamps, bit by bit by bit. And each little bit has a little bit of area, dA, dA, dA. So you have a little, like we were doing sugar cubes, differential sugar cubes, now you can do differential postage stamps. Okay, you imagine you build it up. And so the fluid is pressing on each little patch. And so as you add in patch by patch by patch, as you build the shape up out of little postage stamps, the total force on this area is going to grow because each little patch receives a little bit more force. So what you would define is the pressure is the derivative of the force on the shape with respect to area. So as you grow and you make the plate bigger, the fluid pushes more and more and more, and the pressure grows. Has anyone, when you go down the highway, you stick your hand out the window, okay? You can feel the pressure, you can feel the force on your hand, okay? So as you're going down the road, you stick your hand out, you can feel the force on your hand. What do you do to increase the force on your hands? Turn it, right? Well, what's happening there? More area, yeah. So it's by growing the area, you've grown the force. So the rate of change of the force, right? The rate of change of the force with respect to area would be pressure. However, just like, so that's the general formula. And if you had something which was turbulent, so crazy flows, you could imagine a situation where the pressure would vary at different points in the pipe and it would be complicated. We aren't going to have any of that. So for us, just like for density, we could assume, or I could simplify to uniform situations. We'll have the same thing here. For us, for a uniform, which means everything, the rates of change are all going to be constant. Uniform fluids, we could just say we're going to have that the pressure is the force divided by the area. So it's force per unit area. We'll just divide them. It'll be that simple. Okay. Questions about that? So you can turn it around, and then you could also rework it and say the force from a fluid is given by the pressure of the fluid times the area of the object. And it's the area that is touching the fluid that would be important. Okay. Questions about, does that seem okay? So let's think about that. When I push down on my hand, I push down and I feel a certain amount of pressure. If I do this, why does the pressure, I push just as hard, why is the pressure I'm feeling bigger? The area is smaller, right? You're squeezing that entire force, you're concentrating it into a little area, and therefore the pressure goes up. Okay? So that's the idea there. So unit-wise, what would be the units of pressure? Be civilized. Come on, Gabe. Yeah, that's what you're fine. So pounds per square inch. So Gabe said pounds per square inch. Now, what kind of pound are you talking about? Pound of force, because this is a force. Okay, yeah. We'll talk about pounds of mass and pounds of force. So we have, I'm going to write that LBF for pounds of force divided by area. And so in the US, a lot of times people use inches as length, so inches squared would be pounds per square inch. Sometimes that's written as what? What's the abbreviation we get? PSI. PSI, pounds per square inch. Very good. If we're being civilized, actually, even before we go there, what other unit could a barbarian use? You're not using inches, what else might you use? Feet? Okay, so instead of PSI, you might have PSF, pounds per square foot. So, or LBF divided by feet squared, which is known as PSF. This course will have, half the problems in metric, half the problems will be in bad units, in English units. So we have to get used to going between them. So let's do that. Take a second and let's convert 1 PSI to PSF. Let's go through that just to practice, make sure everyone knows how to do that. 1 PSI to 1 to PSF. Pounds per square foot, pounds per square inch to pounds per square foot. All right, how do we do that? Well, these are nice, they're faster to write than fractions and stuff, but you really need to remember that this is a fraction. That's what it means. So this would be 1 LBF over inches squared. And I want to get rid of the inches and replace it with feet. How would you do that? Squared. Don't forget the squared. That's the big one. Okay, so you want to multiply this. So remember that there are 12 inches in 1 foot. So my unit ratio will be 12 inches over 1 foot squared, so that these units cancel, and I'm left with pounds per square foot. So that is 144 PS. So the conversion is 144, which kind of makes sense, because remember, because as you're going from square inch to square foot, you're growing. 1 square foot is made up of a whole bunch of square inches, so it's gonna get bigger. Okay, what would be metric units for pressure? What would be metric units? Well, that's a name, but what would be in terms of fundamental or more fundamental units, what would we want to make it? It's supposed to be force over area, so what would be the natural unit for force? Newton. I mean, you can go all the way to kilograms and meters, but really newtons. And then what about area? What would be the natural unit there? Square meters. So another civilized set of units would be newtons per meter squared, and you can convert that to kilograms, whatever you want. And that we give a name. It is defined to be a Pascal. And symbol for that's PA, Pascal. So 1 Pascal is 1 Newton per meter squared. Those are the metric units that we have. Okay, so fine. There's another unit you guys would have heard of in chemistry class, maybe even more, to measure air or to measure pressure. Bar. Okay, you could have bar. So one is really common in everyday situations. ATM, what is it, like for money? Atmosphere. Yeah, atmosphere. Yeah. So at STP, but really on a normal day, everyday situation, the pressure is on average 1 atmosphere. Okay, so that's a typical kind of room setting, 1 atmosphere. So that typical day, that typical situation, we have atmosphere. So we can, 1 atmosphere is the pressure on a typical day. Does anyone remember or know how that relates to any of the other numbers? It's okay if you don't. 1 atmosphere is the same as 101.3 kPa. What is that? Kilopascal. So it's 101,300 Pascal. Okay, so just so you know, like what's the range? We all know, or I think most people know, that when you have like a stormy day, the pressure drops typically. So that raises the question, okay, if a normal day is this, to kind of get a sense for our range of existence, what is a day like today where it's raining and storming? It's probably like 99 kilopascal. Maybe 98 would be really low. I mean, that's kind of the range. And on a high pressure day, might be 103. So that's, we kind of live in a pretty narrow band. Plus or minus 2. Okay, so that's what you get. And then, does anyone know what an atmosphere is in PSI? No? Turns out that's 14.7 PSI. So that allows us to convert. I mean, we can go all the way from the fundamental units, but this is faster than going all the way to meters to feet and feet to inches and kilograms to pounds of mass, or newtons to pounds of force, if you want to think of it that way. That's a much longer chain. You should learn to just know these numbers. We will use them all the time when we're coming up with typical examples. We'll talk about a machine. Where's the machine working? Working in a garage. What's the pressure in the garage? Assume it's 1 atmosphere. Right? So we will use these numbers a lot. It's useful to just know these conversions. Okay, 14.7 PSI. Okay. There are some other weird ones. There's a unit called a millimeter of mercury. You guys heard that before? You guys know where that comes from? Why you use that term? It's okay. We'll talk about making barometers here a bit later. You'll understand why millimeters of mercury. But it turns out pressure at 1 atmosphere is enough to support a column of mercury, which is 760 millimeters. So 1 atmosphere is 760 of mercury. And there's another, if you do millimeters, you can do inches, and that is 29.9 something. 92 inches of mercury. Cool. So when we talk about measuring barometers and how you can measure air pressure or pressures, I'll explain that a bit more. But it just turns out pressure is enough to support a column of mercury, which is this tall. And then if you increase the pressure, you can increase the column of mercury that can be supported. And if you decrease pressure, it decreases. And so you can use the height of the column that is supportable as a measure of the pressure. Okay. All right. So, okay. So, let's talk about some properties of fluids and how they relate to pressure. First thing I want to do is kind of make an idealized sort of mental pressure gauge you could imagine. My little pressure gauge is going to look like a cup with a spring and a movable surface, and we're going to assume that it doesn't leak. So it's an idealized thing. So I'm going to imagine I've got a little pressure gauge with a spring, and then you can imagine there's a movable face that could, so if you increase the pressure, it would compress the spring, and if you decrease the pressure, it would expand. Something like that. You can imagine a little scale that would allow you to do that. So in my mind, let's just imagine that that's sort of device you could have. That's not how we're going to do it, but you can imagine such a thing. Okay, and we're going to imagine it's really small. So hold on there. Let's make the face of this thing be round, and it has an area, and the area of this we're going to just say is little, so it'll be like DA, just a little tiny patch. Okay, you can have. So this would allow you to measure the pressure locally inside the fluid because it's tiny, it's differential. So you have a big swimming pool, you could drop this in there and define a pressure at each point in the fluid. So what we're going to do is imagine that I have a fluid. Think of it as a tank of water. It could be anything. And I'm going to imagine that it's stationary. So I assume it's a stationary fluid. It's not moving anywhere, just stationary. And what I'm going to do is imagine that I very carefully drop in a lot of these pressure gauges. Now that's kind of bad. It just occurred to me that swimming pools and pee gauges, that could take 2 meetings, but I'm talking pressure here, not bodily fluids. So there are no little kids around peeing in the pool. So I'm going to drop a whole bunch of these, and I'm going to just imagine that I drop them down, one here, just kind of next to each other. And you can even imagine that they're in contact with the fluid and also themselves, and everything's in equilibrium. Okay, nothing's moving all the way across, all the way across. Okay, so just imagine I suspend them, and they're in equilibrium. And what you would know, because it's not moving, and if they're all identical, that means the pressure coming from the wall on one of them must be the same as the pressure coming from the fluid on another one. But then that means, since that fluid bubble isn't moving, it's the pressure, the force on it from the other gauge is the same. So what I'm getting at is, to go across, just number them, the pressure along a horizontal slice in a stationary pool of fluid must be the same, using Newton's third law, using equal and opposite forces. Okay? And it's really the second one, it's both, right? They're not moving, so the net force on this guy is 0, which means the force from the left is the same as the force on the right. But then via Newton's third law, the force coming from the right is the same as the force from the gauge on the blob of liquid, which using Newton's second law is the same as the force coming from gauge 2, and so on. You can just kind of daisy chain your way across. So the pressure, so in you want static equilibrium, the pressure is constant along horizontal slices. So if we have a pool and you go to a common depth, the pressure will be the same. If it's not moving. When things move, it changes. How can we use that? Let's take a second. Let's make a funny jar or tube. Let's start really simple. Let's imagine I have a tube. It's open to the air. And I'm going to fill it with, and this is open to the air. If I tell you that on the left-hand side, the water level is here, where is the water level on the other side and why? Justify it. You might know from everyday experience, but why? Use this fact to help you. And this is like in this room, like a normal situation. So you're saying it's going to be like right here. Okay, and then does everyone agree with that? Yeah, I agree with that. And why? Okay, with the same pressure, the pressure has to be constant, same depth. Do we know anything about the pressure here? Why?
It's an open container.
It's 1 atmosphere. You would just assume it's 1 atmosphere. So if you know it's 1 atmosphere here, and you know it has to be 1 atmosphere where it contacts the air. Wherever it touches the air, it has to be 1 atmosphere. Therefore, they have to be at the same depth. What is the assumption that lets you know that wherever the fluid touches the atmosphere, the pressure is 1 atmosphere? Or whenever the fluid touches the air, what's the assumption that lets you know that the pressure has to be 1 atmosphere? What were the caveats that I started with? Equilibrium. Right? So if the fluid's in equilibrium, then that means that the pressure that the air pushes on it, it's pushing same with the air. So that equilibrium is the assumption. It tells you that yes, the air is at 1. We know the air is going to be at 1 atmosphere, but in equilibrium, the fluid has to be balanced with it. If it was out of equilibrium, it could be like in the middle of an explosion and the water could be shooting out. That's different. You can't make all the assumptions. But when things are stationary, static, or really, they don't even have to be 100%. This is a good approximation if it's slowly. As long as it's slowly changing. Pressure, here's the air, and wherever this is also has to be at air pressure. And because those are the same numbers, then the height has to be here. Okay, does that make sense? So along a horizontal slice, no matter the shape, I didn't say anything about the shape. So you could have a tank which is like this. Where should the level be? Well, they're both open to the air, so it has to be the same. Shape does not matter. Okay, that's a little confusing. That's true. All right, just think about that. All right. Okay. Another thing. We kind of use it up there. The force on these little gauges from the left, because they're in equilibrium, is the same as the force to the right, right? Which means that locally inside the fluid, the force is the same in all directions. Now, the force, that doesn't mean the force is constant everywhere. Depends on the state. Is the pressure going to be the same at all depths? So the pressure is going to change when you move up and down. But if you stand at one place and you look in different directions, but keep the depth the same, just look in different orientations, the pressure is uniform. So the pressure is going to be the same, if I kind of stare in different directions, the pressure is going to be the same in all directions. Now, the actual number for the pressure changes as you go up and down, but it'll be the same in all directions at each point. Is that okay? So That's, so then, okay. In a crystal, that can sometimes be different. Like in a solid, you can have a different pressure, like along a principal axis of the crystal versus across it, things like that. Or like in a beam of wood, it might develop pressures differently across grain or along down grain or like along grain. But in a fluid where you don't have any of that structure, there's no, a little droplet of fluid doesn't know the difference between X, Y, and Z, so therefore the pressure has to be the same in all directions. Okay. So that's kind of an interesting thing. So that means that, you know, if you go swimming, the pressure at a certain depth would be the same, you know, as you move your head around. That's kind of interesting thing. All right. Okay. Any questions about that? Now we're going to come to actually getting the formula for the depth pressure. Okay. So what I want you to imagine is you have water, and this would be a static pressure because it's the pressure you'd have if things are stationary, like a column of water that's stationary. So imagine you have a column of water or some sort of fluid. We'll assume the density is uniform. And if I tell you, so there's some liquid here, let's say. If I say that the pressure at the top is some value, P, right, the pressure at the top is some value, we'll call it P top. I ask you at some other depth down, let's call this height H, the height of that column. And I ask, and we'll say that the fluid has a density given by rho. Right? And what I'm going to want is the pressure at the bottom. Now, what do you expect? Do you expect the pressure to increase or decrease as you go deeper? Increase. Why?
More water on top.
Yeah, so if you're standing down here at the bottom, you know, say you're holding the water with your hand, you're supporting not only, you're supporting any downward force, but you're also supporting the weight. And the farther down you are, the more mass you're having to support on top of it. Okay? So, just for simplicity, let's assume it's a straight column and it has an area A. Okay, so there's area A pushing straight down. The area is not going to matter in the end. Let's just imagine. What I want you to do is imagine that you're doing exactly that. Your hand is supporting that column of water from the bottom. You're supporting that column of water from the bottom. We don't really have any new thermodynamics or equations for this semester, but I know that it's in equilibrium. What does that mean? When something's in equilibrium, I don't mean thermodynamic equilibrium, I mean, what do I mean when I say like physics 1 stuff? What does equilibrium mean? Sum of the forces is 0. Equilibrium means no acceleration, right? Okay, so now imagine your hand is there kind of holding, supporting that column, okay? Right, so what we want to know is the column of water is in equilibrium, right? It's not moving, there's no net force. So what are the forces acting on that column of water I'll go ahead and shade it in. We're talking about this body of water from your hand up to top there. Okay. What are the forces acting on this water? Gravity. Anything else? My hand. Anything else? What's at the top? Some pressure. But if there's a pressure, there must be a. What is the pressure? It's a force per unit area. So if you have a pressure, there's going to be a force. I didn't say that it was an atmosphere. If that was air, then yes. But what if it's like a pressurized CO2 cartridge or something? So because there is a pressure, there is some sort of force there. So, okay. So I have three forces acting on this blob of liquid or water, whatever you want it to be. How do you analyze systems of multiple forces? What do you do? Draw free body diagram, right? So let's draw a free body diagram for that column of water. Let's label the forces. So there's my water. What are the forces? Well, there's a force from my hand. Which is really, I said my hand, but really it's just the force at the bottom. My hand just stand it to help you. Well, it really doesn't matter. It just, there's some force coming from the bottom. That's all I really care. It could be coming from, let's say that was the bottom of the tank. Well, then it would be a normal force. It could just be the next layer of fluid. So it'd be some sort of, maybe you call it, it doesn't matter what you call it, but it's some sort of contact force. Okay? What else do we have? Gravity. So we have a weight of the fluid. And what else do we have? Well, this is a force diagram, a free body diagram, so we need a force from the top. Okay, so there's going to be another force going down, some sort of force from the top. Okay? But you're anticipating the right way to move this. We want to convert statements about forces into statements about pressure. So that's where we're headed. Okay. It's in equilibrium. So what does that mean? All right, so the net total force, the net force is 0. So that means that the upward force cancels the downward forces, yes? So that tells me that the force at the bottom, if I write it with positive magnitudes, right, the force at the bottom has to be just as big as, so the upward force has to be just as big as the downward force. So I'm writing out positive quantities here. Force coming from the top plus the weight. Awesome. And what was the assumption that allowed me to write this? Equilibrium. All right. So when you start relaxing these words, so what's going to happen is you read some story about blah blah blah, fluid in a pipe, blah blah blah. First question: is it a rest or not? These little words tell you what you can assume or not. It doesn't matter. Okay. Okay. Well, all right, great. What's the, and I said, what was the goal? We don't want to talk about forces. We want to turn it into pressure. So how do you turn a force equation into a pressure equation? How do you relate pressure and force? Force per area is the pressure, which means force is pressure times area. Okay, so this would be pressure at the bottom times area equals, what do I do for this one? How do I rewrite that? Well, it's just going to be pressure at the top times the area. A area. The weight of the fluid. What's the formula for weight? mg. All right, okay, great. But you know, I got rid of forces using pressure. I kind of want to get rid of mass and write it with some other property. What is mass related to? Density. How is mass related to density? How do you go from density to mass or mass to density? What? Just tell me. What is divided by volume? Mass divided by volume is density, so therefore mass is density times volume. Okay? So this is going to be density times volume times G. What's the volume of this cylinder? Of area, cross-sectional area A, and height H. The volume is just going to be A times H. Cross-sectional area times the height gives you the volume. And we arrive at our key formula here because the areas cancel. And we learn that the static pressure at the bottom is the pressure at the top plus the density of the fluid times G times the depth H. Okay. Questions on how I got that from the chain of reasoning? We'll have similar kinds of logic where we convert one thing to a density and whatever, divided by the areas and get similar equations. Let's do one example and then we'll take a mass break. Tell me, what is the, let's say you have a swimming pool. And let's say the depth of the swimming pool is, let's say 2 meters. It's filled, we'll just assume pure water. So what I want to know is, what is the pressure at the bottom? Of that pool. So you can use the numbers for standard scenario, right? So we're going to assume the water has the density of just pure water, which is what? What's the water? We did it last time. What's the density of water? 1 gram per cc, but we want 1,000 kilograms per meter cube. Remember, right? If the density, if it was 1, you could lift a fish tank easy. Okay, so the density is 1,000, and what's the pressure? Yeah, assume it's stagnant water. But this is a situation where even if it was not, if it was only slowly moving, this would be a good, you could still use this formula and it would just be approximate. We will incorporate velocity later and you'll see. It makes like a tiny percent. Okay, and what's the pressure at the top? 1 atmosphere. Now, one other simplification. What was 1 atmosphere in metric quantities? What is, so 101.3 kPa, what do you wish that number was? I wish it was just 100. And we know that that is within our range of typical days. So many times in many problems, they'll just say 1 atmosphere is 100,000 kPa, or sorry, 100,000 Pascal or 100 kPa. Depends on the accuracy of the problem. So you have to look at the details of the problem. If they're giving you really rounded numbers, just use 100. If they're giving you detailed numbers, do 101.3. Okay. All right. So find the pressure at the bottom, and give your answer in atmospheres, though. So compare it to the pressure at the top in nice numbers. Give the answer in atmospheres. But you should do your work in the metric system. So anyone who doesn't see what they're supposed to do, everybody see how to do this? So we know the pressure at the top, 1 atmosphere. The density is 1,000. We know G and we know H is 2. Pressure at the bottom. So really, just make sure you get your units correct. And at the end of the day, I want you to come back to atmospheres. Does anyone have a number? Stuck. Let me know and I'll come out. Otherwise, I'm going to start working through it. Okay, so in a situation, I would say the pressure at the bottom, the pressure at the top, which is 1 atmosphere, which well, I'll put in all the numbers, but I need to write that in Pascal. So it'd be 101,300 Pascal newtons per meter plus rho GH. And rho GH in metric unit, it'll come out in Pascal. If you use standard metric units, it'll come out there. So that would be 1,000 kilograms per meter cubed times G, which is 9.8 meters per second squared, times the height, which is 2 meters. Good so far? Okay. And so this is going to be about 20,000. Right? A little bit more than that, 19.6 thousand. Is that what you get for this term right here? Okay. So this is going to be, but I'll show how the units work. 101,300 Pascal plus 19,600, and then I'm going to get, I have a kilogram. So I actually get a kilogram per meter second squared. What is a Newton in metric units? That's going to be a kilogram meter upstairs per second squared. So this is the same as a kilogram meter divided by a meter squared second squared. That's a Newton per meter squared. It's Pascal. So it comes out. So I multiply and divide by a meter to recognize it as a Newton per meter squared. So that this is a Pascal, it turns out. So now I add it together and I get 20. So I get 129 Pascal, which is pretty close to 1.2 ATM. Does anyone have a more accurate result? is this, did anyone get this? Make sure I got that right. That's what you have. Is there anyone who did not get that? Does anyone have something way different? You're looking troubled.
Yeah, I didn't get it.
What did you get? Do you have this line?
I had up until the 1,000. And I forgot to grab the.
Got you. All right. So then you're getting my smaller effect. Yeah. Okay. All right, so you just gotta watch all the little bits and put them in there. When you use the metric system, it comes out nicely. When we start using other units, then you have extra fun with unit conversions on top of this. That will come. All right. So we're going to take a 5-minute mask break, and then we'll do some more examples. Okay, so there we go. All right. So similar kind of problem. Use some of these facts. But imagine we have one of these tubes, kind of U-shaped. I'm going to change it a little bit. And what I'm going to imagine is I have a tube. I'm going to fill it with water. It's going to be shaped like this. So this is open. This is not. Okay, this is open to the air on the left. It's closed. It's capped. And what we're going to do is I'm going to tell you that this height on the left, let's just make it 1 meter. And this height is 0.75 meters. And we're going to use water, so let's just use pure water. And you can make standard assumptions about the air outside. Okay, so what does that really mean? 1 atmosphere outside. What I want to know, and what I also am going to tell you is that this cap right here has an area of, actually, I'm going to say it's circular. It's a circular cap. I'm going to say it has a diameter of 3 centimeters. There's a diameter of 3 centimeters across the top. I want to know what is the force on the cap coming from the fluid. That sounds totally different. But it's not. It's the same skills, and at this point we basically have like one equation. So you know it has to boil down to that same equation, really. Trick is to kind of massage this question in this scenario into things you've already seen. Okay. Let's kind of step through this here. We want the force coming from the fluid. But our equations don't really give us forces. So what do we really want to find and then use to get the force? What quantity is related to a force but not quite the same? Pressure. So really we want the pressure here. So the problem is really about finding the pressure. All right. And, okay. That's fine. So we want the pressure right here. And how do I go from pressure to to get force? Pressure is what? Pressure is force divided by area, so therefore force is pressure times area. So we need to find the area of this circular cap. How can you find the area? Pi r squared, right? So you've got the diameter. So you can get the area. Good. All right, so there you go. And then, okay. So that's one thing. And we'll take a second, find the area first, because you're going to need to find the area of that end cap, and then we'll talk about how you go from there. Step one is area of the cap here. You said it was pi times r squared. What's the radius? 1.5. Do I just do pi times 1.5 squared? What else do I have to do? Get it in civil engineering. Yeah. So we want it in meters. So we want to do pi times 0.015 squared, and it'll come out as meters squared. Someone who's done that, what do you get?
7.069 times 10⁻⁴.
It's tiny because a meter squared is this big, and we're talking about a little thing, so it's going to be tiny. Now, here's how could I use what I know about pressures along horizontal lines when things are static? They're the same. So that means the pressure here is the same as the pressure where? Here. So the pressure here is the same as the pressure here. And we can use that logic a lot to help us. Sometimes it looks like you don't have enough information. If you use that fact, it'll help you. And what is the height of this column of water? 0.25 meters. So we know the rho, we know G, we know H, and we know the pressure at the top. So we can find the pressure at the bottom at this point, and then that has to be the same as the pressure right here. Okay? So we use our equation, the one I just erased. Pressure at the bottom is pressure at the top plus rho G H. We use the appropriate height. That gives us the pressure at this point, and we use the horizontal rule to find the pressure at the cap, and then I can get the force. Everybody? Good. Yes, Gabe.
Rho, the symbol for density.
Rho is the symbol for density. Yep. So kind of piece those bits together and use them to figure out what is the force from the fluid on that cap. This is only the force from the fluid. You would also have the force from the ambient air pushing down, and you would the difference between those would have to be supplied by the well, the joint, or however it's fitted together. And it's if the difference in pressure from the air and the liquid is too large, the thing pops. I would say work it in metric, so Pascal, and then afterwards, just leave it Pascal. Yeah, give your answer in Pascal. I'm just gonna kind of lay out the steps now, and then you need to fill in the details. So we would use pressure at the bottom, pressure at the top, plus rho G H to find pressure at the bottom on the left. And once you know that, then use horizontal rule to find pressure on the right, and then use force is pressure times area. Those are our steps to work through. Pressure here, but that's coming. So what I would do is first find the pressure kind of on this horizontal segment. Just transport it across. Yeah, okay. Yeah, because it's not, it was moving. Well, I mean, it has to be moving a lot to really change it. Well, it's open to the air, so it's in one atmosphere. You're trying to find the pressure on the right. You know the pressure on the left is air at the top. On the cap, oh, you got that. The cap is over here. No. The left-hand side is open to the air. The right-hand side has the cap. Yeah. Yep. The left-hand side is open to the air. Okay. How many people have a question? The pressure at that point from the fluid is the same in all directions. Okay, so let's go through this. So I first want to find the pressure on the left, kind of at 25 centimeters down. So I would say pressure on the left at the bottom is 1 atmosphere plus the density. And I know the units are going to come out as Pascal because I just did it in the previous problem. So 1,000 times G times the height. The height of the column that we're focused on is not the whole meter. We only want the difference of the two heights. So we only want the 0.25 meters. And so that gives me pretty close to 2.5 thousand Pascal. So I'm gonna get something like 103. What number do you get? Okay, 750. We don't usually need that much accuracy on these things, but that's okay. Okay, does everybody agree with that so far? All right, so that's the pressure down 25 centimeters, which is using our horizontal rules, the same as the pressure across. Awesome. And so to figure out the force coming from the fluid pushing up, it is the force is the pressure times the area equals 103,750 Pascal times the area in meters squared. You have to get the area in the right units. 7.069 times 10 to the negative 4. And it'll come out as what number do you get?
Got 7,334.
7,334 newtons. Okay. So we multiply all that, right? That seems about right. Wait a minute.
I only got, I got 73.
1, 2, 3, 4. It's got to be 7. Yeah, that seems good. There we go. Which equates to, that's like holding about 7 kilograms in your hand. So, you know, in terms of the equivalent scenario. So, all right. Let's see. Let's do another one. Thing. So does anybody, all right, check the tire pressure? How does that go on your car? How's the gauge, what kind of happens there? All right, right? And you have to do the sound, that's really important too. Okay. So let's imagine we're gonna make our own little device here. Let's imagine that I have a tire. And what we're going to have is some sort of, you know, you have a stem coming out, and we're going to imagine we have a little column like a little device, and we can imagine here, let's see, let me think about what I want to say. So here's what we're going to do. We're going to make this kind of weird. We're going to go ahead and cap this in. Okay. And you think about what would happen. We're going to imagine that there's like, first off, we're going to imagine there is there's mercury in here. So there's mercury inside. And we're going to imagine that it goes up, 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 and there's nothing there. There's vacuum. There's nothing there. So if there's vacuum, what would the pressure be at this point? It would be 0. Okay? So we're going to assume it's empty. up there. And we're gonna assume, this isn't very realistic, but kind of gets the idea across. We're gonna assume that there's one atmosphere here. Okay. I want to know what is the height, or really what's the difference in heights of the column of mercury supported by this gas. Think about what you know. There's gas or air in here, right? So what's the pressure right there? And they're in equilibrium, so what's the pressure in the mercury right there? So what's the pressure right here? What's the pressure right there? 0. So the pressure at the top is 0. Pressure at the bottom is 1 atm. Find the height. If you remember, you might know the answer. That's where that comes from.
So it's the height from the bottom of the set to the.
It would really be this, but when you make these, so this is called a manometer, this type of pressure gauge, this kind of device. And this part is always negligible. So but you're always looking at the difference in heights. You'll need to know the density of mercury. Mercury fills this region. What's the density of mercury? 13,600. Yeah. Density of mercury. 13,600 kilograms per meter cube. Through that. Pressure at the bottom. Did you give me anything?
Yeah, you put a yellow on it and then Jimmy's done a drill to take
Pressure at the bottom is pressure at the top, plus rho G H. What is this number? Pressure at the bottom, 1 atmosphere, or 1,300 Pascal. Pressure at the top is 0, plus the density, 13,600, times G, 9.81, times the height. Solve for the height. And it'll come out in meters when we do it this way. What'd you get? Michael, what'd you get? 0.759 meters. Or if I did it in millimeters, I might say it's 759. I think earlier I said 760. Millimeters. Remember, I said that 1 unit of pressure was millimeters of mercury. So it was the height. You're measuring what height of a column of mercury could be supported by an atmospheric pressure. That's where that came from. You could also work out units like millimeters of water. But well, we kind of know because the density of mercury is 13.6 times bigger, if you use water instead of mercury, your column of water would be like 13 meters tall. It's taller than the building. So that's why no one uses water as their fluid of choice, you're using mercury so that it can be compact. You can convert it to inches and you'll get 30, 20 pounds. So that's where that comes from. This sort of device is called a manometer, where you have a column of liquid that's supported. All right. Okay, one last term, like a definition of a quantity, and then we'll be done for the day. What I've talked about, the way I've introduced pressure is so far is something called absolute pressure. Basically, when we had vacuum, it was zero. Right? That's an absolute pressure. That's not the pressure that you normally see on something. When you fill up a tire, what pressure do you fill it up to? Like a car, typically. 35, you know, people do different amounts, but roughly that. 35 PSI. That is actually the difference between the environment. So in actuality, you know, the environment's 14.7. That's one of our numbers. So in actuality, it's 35 plus 14.7 in absolute. The absolute pressure is. So we call that relative amount to the atmosphere a gauge pressure. So people talk about pressure ABS, or sometimes people will write, when they give the units, instead of PSI, they'll write PSIA. That means pressure absolute, as opposed to a gauge pressure. So absolute is 0 in vacuum. Right? In vacuum, you assume there are no little particles bouncing off the wall, so there's no force on the wall, so that pressure is 0. Pressure, the gauge pressure, is a pressure gauge, like on a tire, would read 0 when the inside and outside are exactly the same. So it's the relative pressure from 1 atmosphere. So that means it's actually the absolute pressure minus 1 atmosphere. You have to convert it to the right units. But, so maybe with Pascal, that's the idea. So that if the inside of the tire and the outside and the air are exactly the same, the gauge pressure, the gauge will read 0. That's a flat tire. What about if you go less than an atmosphere? What do we call that scenario? Vacuum. A vacuum. So we can talk about a vacuum pressure. And I should be more careful. When I said vacuum here, I really meant like 100 real vacuum, like ideal vacuum. But any deficit less than 1 atmosphere is like a vacuum cleaner. It's a partial, it creates a suction. So now, when people talk about vacuum pressures, they don't want to talk about negative numbers. So by convention, they arrange it so that you always get a positive thing. So a vacuum pressure would be 1 ATM minus the absolute pressure. Okay, so if the real 100, the absolute pressure was less than 1 atmosphere, so let's say it was 0.9 atmospheres, then your vacuum pressure would give you a positive number there. So depending on your application, you're going to use whichever of the, like when you talk about gauges and things, they're going to use whichever one of these gives a positive number. So if you're pulling a vacuum, your gauge pressure is going to be negative. If you have positive pressure, then your vacuum pressure would read off negative. So they're going to use whichever of these is positive. Okay. But devices that we measure, like the devices you're familiar with, those are all measuring relative pressures. So now, sometimes they kind of reverse engineer and convert the scale, because you just have to add this to get back to, you just add 1 atmosphere to shift it. But physically what they're doing is looking at differences in pressure. So they're actually measuring gauge pressures in actuality. Okay, so next time, we'll talk a little bit, maybe a little bit more about different kinds of gauges, what goes into them. I have some examples I can bring out. And then we're going to talk about buoyancy and car lift, and then we're going to work towards something called Bernoulli's equation. So Bernoulli's equation is going to be how you generalize this pressure equation to incorporate fluid flows, like velocities and stuff. And then we'll move on from there. Okay, so that's it for today. I will talk to you later.